Many times you'll have a configuration consisting of multiple charges and you need to calculate the net initial force on each charge. Now the reason why I said net initial force is once a charge exerts a force on another, it's going to move. And you're not going to have a static setup. So we just want to know initially what happens. Which way is the initial force on the objects, and then after that it gets very complicated and we're not going to work that. And we're only going to deal with a few charges here. We're going to do an example with 3 charges. Again, this is somewhat not terribly realistic, but it gets you used to the mathematics. There won't be any problems as part of this presentation for this section because they go on too long. However, the classwork and homework problem sets will have several of these that you should absolutely practice. So let's start with 3 charges in a line in one dimension. So what we have here, we have one charge, negative 10 microcoulombs. Remember micro? That's 10 to the minus 6. Here we have a 15 microcoulomb charge, and over here a 25 microcoulomb charge. We have a fancy name for this process, and it's called the superimposition of electrical forces because we're adding forces together. There's a procedure for doing this, and I'll show the process first, show a couple of the steps, and then we'll work the problem. We're going to assume that all charges other than the one that the initial net force is being calculated for are immobile. They're not moving. This will allow the determination of the direction of the individual initial forces on that one charge. Don't worry if this isn't making too much sense to you at the moment. This will serve as a nice reference to you once we go through the problem. And then, since we're dealing with forces, free body diagram. Free body diagrams never go away in physics. We'll draw one for each charge using the fact that opposite charges attract and like charges repel. Continuing our process, we will use Coulomb's law to find the magnitude of each pairwise force. We will then sum the forces for each charge. Now make sure you take into account that they are vectors, so they will have a direction and a magnitude. And we're going to use the free body diagrams from the previous page to assign signs to the forces. If they point to the right, they're positive. If they point to the left, they are negative. We do this because Coulomb's law is just finding the magnitude. It's not giving the direction. We have to find the direction by looking at the charges themselves. So for example, if we have a positive and a negative charge like this, we know that the force that the negative charge exerts on the positive charge will move it that way. Also, the positive charge will be exerting a force moving the negative charge this way. The magnitude of these forces are exactly the same, but they're in opposite directions. This we will call a negative force because it's going to the left. This will be a positive force because it's going to the right. We have a labeling convention so we can keep track of the forces. F of 1, 2, and notice that this is in bold. That means that this is a vector. That's another way of showing a vector without the arrow. This is the force that Q1 exerts on Q2. F of 1, 3 is the force that Q1 exerts on Q3. Then of course F of 2, 3 is the force that Q2 exerts on Q3. By application of Newton's third law, the force that charge 1, 2 the force that charge 1 exerts on charge 2 is the negative of the force that charge 2 exerts on charge 1. Their magnitude is the same, they're just in the opposite direction. And here are the other two types. You may see other textbooks and websites that use a naming convention that is opposite this one. For example, F12 would be the force that 2 exerts on 1. Well, we're not going to use that convention, we'll use this one. Either one works, just follow your instructor and stay consistent. Now it's time to work the problem. The problem is to find the initial force on each one of these charges. What's the first step in any force or dynamics problem? Discuss and then check the next slide. That's right. Well, hopefully. Draw free body diagrams for the forces acting on each charge. So let's look at Q1 up here. What is charge 2 going to do to charge 1? Well, this is negative, this is positive. It's going to move Q1 this way. So the force that 2 exerts on 1 will be to the right. Notice, since I'm working with charge 1, I'm going to assume these two guys aren't moving. I just care which way he's going to move. Which way is charge 3 going to affect charge 1? Well, they're both positive, so they'll repel. So charge 1 will move to the left. So the force that 3 exerts on 1 is to the left. And I'll just let you guys, you can pause the video if you'd like, and verify that all these forces are in the right direction. But before we go there, let's just look at this guy here. The force of 2 on 1 and the force of 1 on 2. When we use Coulomb's law, which is just calculating the magnitudes of those forces, you're going to find that these two are exactly the same. And that's what we want you to do. Find the magnitude first, and then the sign for the force we're going to determine from the free body diagram. So F of 2, 1 will be positive because it's going to the right, and F of 1, 2 will be negative. So again, Coulomb's law just gives us the magnitude. When we add up the forces, we have to look at the free body diagram. Time for Coulomb's law to find the magnitude of the forces acting between each pair of charges. So let's again look at force 1, 2, which is the negative of force 2, 1 when it's a vector, but the magnitude is exactly the same. So we have K, 9 times 10 to the 9th Newton meters squared per Coulomb squared. We then input Q1. Q1, 25 microcoulombs, which is 25 times 10 to the minus 6. Q2 is minus 10 microcoulombs. Put that in here. Notice how we really don't care about the signs. I'm just doing this for mathematical completeness. We're going to take the absolute value. So we're going to wind up with a positive number. And then the distance between charges 1 and 2, well, you can do it two ways. You can do -8 minus 0, get -8, and you're going to square it so you really don't care about the sign, or you can just count 1, 2, 3, 4, 5, 6, 7, 8. So we put 8 down there. It's in meters. We calculate all the math, and we get the force between charges 1 and 2 is 3.51 times 10 to the minus 2 newtons. And again, please pause the video, check these numbers, and find the force between 1 and 3 and the force between 2 and 3. Just one quick thing. The distance between 1 and 3, again, you can count, and you start at -8 and you go to 4 and you get 12. You just count 12 marks. Or you can do -8 minus 4 and get -12. Or you can do 4 minus a -8 and get 12. The distance is 12. So make sure you do that right, and also don't forget to square the distance between them. Very common error on exams. We now have the free body diagrams up here, which give us the directions of the forces, and we have the magnitudes of each force. And remember, the magnitude of F21 is the same as the magnitude of F12. It is now time to add up all the forces for each charge. So the force on Q1 is going to be the force of 2, 1 with a positive in front of it because it's to the right, and F of 3, 1 will be a negative because it's to the left. So here's the force that 2 exerts on 1. We got that on the previous slide. That's positive. And 3, 1 is going to be a negative. And we find out that the total net force on Q1 is 1.17 times 10 to the minus 2 newtons. Now, which way is that going to move? Well, it's a positive force, so the direction will be to the right. And you have to say that. The force has a magnitude and a direction. For Q2, in this case, the force of 3, 2 is going to be positive. That's this number. And now this time, 1, 2 is going to be to the left, so that's a negative. You can see the negative sign. I add those two numbers, I get a positive result, so I say the force is to the right. Again, these are initial forces. Once the charges start moving, all bets are off. Charge 3, I have a positive force 1, 3, that's this guy. And then 2, 3 is going to the left, that's a negative. I add those two numbers, and I get a negative resultant force. So which way is charge 3 going to move initially? Well, going to move over to the left.